Negative 87 dBFS noise floor on a HackRF One. Most people say that's impossible. HackRF has a reputation for poor performance. Typical setups achieve negative 60 to negative 70 dBFS at best. Chinese clones are even worse. But this is a genuine HackRF One achieving negative 87 dBFS, measured at the Hydrogen Line, 1420 MHz, the universal SETI frequency. That's 15 to 20 dB better than typical. That's 30 to 100 times less noise power. How did I do it? Let me show you. Now let's look at the live signal in SDR++ software. I'm tuned to 1.420.500 MHz. That's the Hydrogen Line frequency, the primary target for SETI observations. You can see the waterfall display at the bottom showing real-time spectrum data cascading down as the radio receives signals. Notice the FFT spectrum analyzer at the top showing the frequency content across the band. The receiver settings are optimized for maximum sensitivity. LNA gain is set to 16 decibels, VGA gain at 20 decibels, giving us a combined total gain of 36 decibels. This is carefully calibrated to pull weak signals out of the noise without overloading the receiver. And now look at that baseline noise floor. It's incredibly clean and flat, sitting well below negative 90 dBFS across most of the spectrum. You can see there's minimal interference, no spurious signals cluttering up the band, no harmonics or artifacts. This is exactly the kind of clean baseline performance we need for detecting faint signals from deep space. This level of sensitivity is what makes the difference between detecting a potential signal and missing it entirely. Every decibel of improvement in the noise floor translates directly to greater range and sensitivity for our SETI observations. Now I'm tuning over to 1.528 MHz. This gives us a second frequency point to test the baseline noise floor performance. You can see the same remarkably clean noise floor here across the spectrum. Now let's run the automated measurement script to get precise quantitative numbers on the noise floor performance. The script will systematically test both frequencies we just observed, the Hydrogen Line at 1,420.4058 MHz and the GPS L1 band at 1,575.42 MHz. Here are the measurement results. For the Hydrogen Line, negative 86.77 dBFS. For GPS L1, negative 87.01 dBFS. Both measurements passed with excellent assessments. The RTL-SDR Blog Vi3 is the most popular budget option, priced around $35. It's the entry-level choice for most people getting into SDR. The RTL-SDR achieves negative 70 to negative 75 dBFS at best. That's decent performance for casual listening and broadcast monitoring, but it's not ideal for weak signal work or SETI observations. The Airspy Mini is a premium mid-range option at around $200. The Airspy delivers negative 80 to negative 85 dBFS with sophisticated RF components and filtering. It's widely considered one of the best noise floor performers in its price class, and a lot of serious weak signal operators choose it for exactly this reason. The SDRPlay RSP1A is a popular mid-range choice priced at roughly $130. The SDRPlay falls in the negative 75 to negative 80 dBFS range. Good performance for the price point with wide frequency coverage from 1 kHz up to 2 GHz. So with our HackRF One achieving negative 87 dBFS, we're actually outperforming even the premium Airspy Mini by several decibels. That's remarkable performance for the HackRF platform, especially considering it was originally designed as a general-purpose transmit and receive platform, not specifically optimized as a low-noise receiver. This level of performance puts us in excellent territory for SETI observations, radio astronomy, and serious weak signal detection work. Let me show you the data visualizations I created from this measurement. This is a waterfall plot, frequency versus time from the actual recording at 1420 MHz. The colors represent signal strength. You can see it's mostly dark blue. That's a clean, quiet baseline with minimal interference. This is the averaged FFT spectrum. The horizontal axis shows frequency in megahertz. The vertical axis shows power in dBFS. The Tyan line represents the average spectrum across 200 FFT frames. The red dashed line marks the noise floor at negative 85.22 dBFS. You can see the spectrum is relatively flat across the bandwidth. No strong, spurious signals or interference spikes. Assessment, excellent. This comparison chart shows the context. The yellow bars represent typical performance for different SDRs based on published data and user reports. Typical HackRF setups, around -65 dBFS. Chinese HackRF clones, around -55 dBFS, significantly worse. RTL-SDR, about -70 dBFS. Airspy Mini targets -80 dBFS. The green bar shows my HackRF with modifications, -85 dBFS. That's 15 to 20 dB better than typical HackRF performance. The yellow annotation highlights this. 15 to 20 dB improvement means 30 to 100 times less noise power. This dual view shows two perspectives simultaneously. On the left, the waterfall over time showing how the spectrum evolves. On the right, the average spectrum showing the frequency content. Having both views together helps identify whether features are persistent signals or just transient noise. This comprehensive 3-in-1 view combines everything. Top, the average spectrum with noise floor mark. Bottom left, the comparison bar chart we just discussed. Bottom right, a complete statistics table. The table shows frequency 1420.4058 MHz, noise floor -85 dBFS and -136 dBm, LNA and VGA gains, total gain 36 dB and assessment excellent. This is the complete picture in one view. All these graphs were generated using Python with Matplotlib and NumPy, processing the actual IQ data samples recorded by the HackRF. The complete code is available in the description if you want to analyze your own SDR data. 4 simple modifications achieve -87 dBFS performance. First, use genuine HackRF. 1 hardware from Great Scott Gadgets. Chinese clones lose 22 dB at high frequencies. Second, wrap the entire device in aluminum foil for RF shielding. Third, add a CPU cooler on top for thermal stability. Fourth, and most critical, ground the aluminum shield to eliminate ground loop noise. Total cost, $12. Performance gain, 15 to 20 dB improvement. That's 30 to 100 times less noise. With this clean baseline, I'm ready for the next phase. Here's where this project leads. This is a hydrogen line feed horn designed for 1.42 GHz, precision optimized for radio astronomy at the hydrogen line frequency. And this is the Discovery Dish, a 1.5-meter parabolic reflector antenna system specifically designed for amateur radio astronomy. I've ordered this complete system, and it's currently being manufactured. It should arrive within the next few months. But the Discovery Dish is just the beginning of a multi-year SETI monitoring project. Subscribe to follow this journey from the beginning.